Good morning, everybody. Hope you're having a good day. So I'm going to get started with Unit 3. I was going to go over the progress check, but not everybody has finished that. So, finish the progress check. Do it. So, today I want to start going over Unit 3. This is one of the most important units in the whole, well, probably the most important unit in all of AP Chem. First off, right, it accounts for 1/5 of the entire exam is just this one unit. There are 9 units, and 1/5 of all the exam is this one. So that's one big reason why it's important. 2, it also has some of the most important concepts for later chapters. This is intermolecular forces and properties. So let's start off by discussing what an intermolecular force is. What is an intermolecular force? And how does it differ from an intramolecular force? Intra means more like internal, right, within one thing, whereas inter means, right, more like between two things. So for example, an interstate is a road that connects two large areas, generally states. It goes across states. Right. Intramolecular that's the bond. The force that holds one molecule together. But an intermolecular force is what holds multiple molecules together. All molecules have intermolecular forces. We have many different kinds. I'm going to go over each of them. We have, in order of strength, ion dipole, hydrogen bonding, dipole, dipole, and finally, London dispersion forces, also known as induced dipoles. So we also call these LDFs. You might see LDFs or induced dipoles. Those both mean the same thing. Now, even though it's right in the middle, I'm actually going to start off by explaining what a dipole is. Because really all of these come down to dipoles. A dipole is, we've talked about this before actually, a result of two poles, when you have polarity, you have one atom and another atom. And when electrons are more attracted to one atom, you have some electrons some of the time here, but not nearly as much as over here. You get one atom that has a partial negative charge. When we have partial negative charges, we draw them like little D's like that. This also results in a partial positive charge because this one is missing it. This is a dipole. How does this affect intermolecular forces? Well, let's just say this was some sort of two molecules. Sorry, some sort of two atoms bonded together, and it's a dipole. So we have a negative, we have a positive. If I have another one of them, then I'm going to have another side that's a negative right here with a positive end, which gets attracted to, oh wait, sorry, that's supposed to be positive end, which gets attracted to a negative end, which leads to a positive end, which is attracted to a negative end, which leads to a positive end, and you keep going on and on like that, all of them linking up with this positive and negative attraction. It's actually a lot like ionic bonds, but they're not full charges. They're partial charges, and so it's a lot weaker. Right, if we talk about our F equals Q1, Q2 over R squared, and for our ionic bonds, right, we have +1 or -1 charges, or +2, -2, +3, whatever, charges for these Q1s and Q2s. For these partial charges, we don't have nearly as high Qs, and so we end up with a significantly smaller force. And so it's not really considered a full bond. But at that point, it's really just our definitions. You could argue over what exactly a bond is. So, let's talk about these, right? Now that we know what a dipole is, an ion dipole is just that, a combination of one dipole. We have the positive and the negative with an ion. So for example, let's say sodium. You can end up with a bunch of, and actually, let me show you what solutions actually look like. And I'll write all these back up later. You know what? No, I'm going to go in order from the bottom. I think actually that will make more sense. Sorry. Let's talk about our LDFs first. Induced dipole. So, whenever you have a bond that is nonpolar, the electrons are going to be shared evenly. However, even that is a matter of statistics. I can actually show you if you look up the density, right, electron density of these bonds. Let's do electron density. Here we go. We call these, right, this is electron density, where if electrons are more in one area, it's red. and if it's less in one area, it's blue. For these ones, we can both see these are two non-polar bonds, and so they both end up being overall green. However, there is always a slight chance, because this is statistics. There is a slight chance for more electrons to just happen to be over on this side, right? On average, they're evenly split because both fluorines or both hydrogens have an equal pull. That doesn't mean they always will be, though. There's always that statistical chance for them to be unevenly split. Most of the time, on average, it will be around both, and so you don't get this property being constant. But let's say you have a really big molecule, though. And all of these have hydrogens on them. Every single one of these bonds is an opportunity for a random dipole to occur for a moment. We call this an induced dipole, or again, the London dispersion forces. All it takes is for a small sample of these molecules to all be having this random chance at the same time. It doesn't have to be on the same thing either, to start seeing the effects of London dispersion forces. And because we have so many atoms in a sample, right? You have a large pile of this. You have so many molecules in that sample that odds are some of them will always be undergoing this. And so it's not nearly as strong as the others because it's induced and then it goes away after a moment, and it's all based on statistics of whether or not it actually happens. Like, for whether or not it actually happens. So London dispersion forces are generally the weakest intermolecular force. It actually has the possibility of being stronger than our other intermolecular forces only if you have a really big molecule, because the larger the molecule is, the more places there are for those randomly induced dipole moments. And so if you're talking about a dipole for a small molecule, and you're talking about a giant, absolutely enormous molecule, London dispersion forces might be higher, right? Just because with so many, one of them is always just going to be randomly having a dipole happen. And when you have a giant sample of them, a giant population, right, you might even have 2 or 3 spots that have it going on at the same time, creating a lot of pull. So London dispersion forces increase between molecules as I can just say like molecular size. Generally, you can say molecular weight gets bigger. But in terms of surface area, because it's not just a matter of these charges forming, they need to actually interact with each other. And you can actually get molecules being so large to the point where it's difficult to interact with, right? So generally, long chains are what work the best for this, for high LDFs. But if everything else is the same, if you're talking about a molecule of the same size, and you're just changing 1 or 2 things, then LDFs, or induced dipoles, are the weakest. But keep that in mind. That is assuming everything else is the same. So I'm comparing 3 carbons in a chain with the hydrogens needed to 2 carbons and then an oxygen, right? If I change one thing here and I make a polar bond here, I'm changing just a single thing that you can see. Changing the one single thing, right, makes it easy to compare. So you won't get a question where you're given a small one and a big one and you're like, which one has more forces? Because you wouldn't be able to know without looking at the actual numbers. But you might be given a question, and I've seen this on AP exams before, that's like, hey, this non-polar molecule has higher intermolecular forces than this polar molecule, than this other polar molecule. What might be the reason? And the reason would be that it's a lot bigger. It's in this long chain that allows for tons of random interactions, and even if they're random, there's so many that it's happening so often. All right. Dipole-dipole. Dipole-dipole is just our standard. That is our normal, right? Positives attract negatives. It's really, really straightforward. It's just, again, polar bonds resulting in positive and negative forces interact with other positives and negatives. So normally how we do this is like a dotted line to show the attraction, to show the dipole-dipole bond. Now we get into hydrogen bonds. Hydrogen bonds are just special dipoles. They are made with hydrogen, which is really our least electronegative covalent element. Hydrogen, ignore that. It's our least electronegative covalent element, and so it creates the opportunity for the largest dipoles. So we're talking about our HNOF. If hydrogen is with nitrogen, oxygen, or fluorine, then it will have a big enough dipole while also being stable enough to create a situation of hydrogen bonds. This actually leads to most of the properties of water, which I'll discuss after this. So for oxygen, we're looking at negative here and positive there. Or for this picture over here, right, we have H and F. That would be a hydrogen bond right there. Hydrogen bonds work the exact same way as dipole-dipole bonds, but they are stronger. And it's not, again, so much that it's stronger in the sense that you're going to see vastly different properties, but you'll see the same properties just increased. And I'll talk about the properties that these cause after I go over each kind and kind of their relative strengths. So, again, the way these look, right, you'd have like a hydrogen here going into an oxygen, and you'd have that there, and that would go into hydrogen. Right, maybe you'd have there, something like that. And actually, it's hydrogen bonding that causes the specific structure of ice when it forms. So let's... Actually, now would be a good time to talk about some of the things that these intermolecular forces do. So a few things that intermolecular... Oh, no, I'll go over the last one first. Okay. Ion dipoles. Ion dipoles is where you have one ion surrounded by a bunch of dipoles. So in water, the oxygens are negative. So let's say you dissolve salt in water. You're going to have a bunch of hydrogens interacting with that positive sodium. Meanwhile, with chlorines, that's really going to end up getting surrounded by positive hydrogens. Right, so you end up having this be stronger than your dipole-dipoles. And again, we'll talk about everything just comes back to this one equation, which is going to keep popping up over and over again all year long. For these forces, right, our London dispersion forces, we only occasionally have charges, so we only occasionally have forces to begin with. And it's going to average out with all the times we don't have forces. For our dipole-dipoles, we have partial charges. For our hydrogen bonds, we still have partial charges, but they're just bigger. Right? And then lastly, for our ion dipoles, we have one full charge and one partial charge. It just keeps pushing the force up. These lead to quite a few properties. Some of the properties this leads to is melting point and boiling point. It's like surface tension, right. Solubility, and more. So for a melting point, in order to melt something, you have to send it from a closely packed solid into a more fluid and movable liquid that can flow freely. The question is, how do we actually do that? I don't know if you ever stopped to think about what's actually holding these together. And what's holding solids together is intermolecular forces. So when you melt ice, ice forms a crystalline solid structure. Right. That looks like this. Now, oh no, sorry, that's ice. That's the wrong ice. We get normal ice. Oh, here we go. We can look at the crystalline structure here. Sorry, there are actually different kinds of ice, so that is one of them. So here we look at our hydrogen bonding for an ice structure. They're all going to be pretty much the same distance apart, forming this repeating crystalline pattern over and over again that spaces them out in kind of the perfect way to make a solid, powerful structure. When you melt them, they're still going to have these intermolecular forces afterwards, but you have to overcome these hydrogen bonds to an extent where they're no longer in this overall structure. So we call this the lattice structure because it's the stability of the solid, but it's given stability based on its intermolecular forces. And honestly, you can make an argument for ionic bonds just being intermolecular forces. But, you know, so it's kind of like overcoming that as well. So, to boil this, right, to melt water, right, you need to overcome that force and allow it to be free-flowing. But once we get to boiling, they are still held close together by hydrogen bonding. This is actually why you feel surface tension. If you do a belly flop, the reason it hurts is because you are using the force of your body to physically push aside these bonds. These hydrogen bonds in the case of water. That takes a lot of energy, which is why it hurts. If you do instead like a pencil dive and you jump straight in with your feet, it won't hurt as much because there's just less surface area and you aren't trying to break apart as much water. So you're using all of your weight and force and speed and momentum concentrated on one small part to break apart a small bit of water instead of your body weight and force spread out across a larger area where you have more hydrogen bonds to break. For boiling, you don't just need to break them, you need to really fully overcome them because it needs to become a gas that is more spread out. At which point, yes, there will still be some intermolecular forces at play, right, when they get close to each other, but for the most part, none of them have those intermolecular forces on them because they're so spread out. So you need to overcome that with enough energy that they move fast enough and have enough energy that they're not being held together anymore. Right, and again, this also affects things like solubility. If something is more polar, it will dissolve better in water. Polar things dissolve polar things. Non-polar things dissolve non-polar things, and this has to do with the presence of or lack of intermolecular forces. All right. So, I'll check the time I have. About 30 minutes, okay. Lastly, I want to actually, more as a fun fact if anything, but show you the chemical structure of cotton. This is the chemical structure of cotton. It has lots of oxygens and hydrogens. These oxygens and hydrogens lead to a lot of hydrogen bonds, a lot of dipoles, and a lot of intermolecular forces. The result of this ends up being wrinkles in clothes. wrinkles in clothes are literally just hydrogen bonds. You can overcome them in the same way you can overcome hydrogen bonds in water with a phase change. You can overcome these hydrogen bonds with heat, with energy. That is why ironing removes wrinkles from clothes. So yes, I can confirm you cannot escape it, and everything is chemistry. Now, hydrogen bonding is one of those things in dipole-dipole, one of those things that are so important that if you take organic chemistry and you are asked a question as to why something might occur, there's a decent chance that like 80% of the time the answer will either be resonance structures like we talked about last week, or hydrogen bonding, or like dipole-dipoles if it's not hydrogen. So I also want to show you, right, athletic wear is usually made of polyesters or, right, synthetic fabrics. So polyester tends to be what is used. If we look up polyester chemical structure, we will see oxygens, but we won't really see those hydrogens and oxygens together. So we don't get those super strong dipoles and hydrogen bonding. That is why athletic clothes doesn't really wrinkle that much. Right, so you can try looking this up. Think of fabrics that wrinkle and fabrics that don't. Right, we think about silk. Silk has nitrogen and hydrogen, right? And it is more likely to wrinkle than polyester, but still less likely to wrinkle than cotton. So think about what fabrics wrinkle, try looking up their chemical structures and see if it's consistent. If something is wrinkle-proof, it is likely because it doesn't really form hydrogen bonds, or if it does, it forms very few of them compared to others. All right. So for the rest of class, I'd actually like you guys to, on AP Classroom, watch the next AP videos. You can watch these ones if you want. I did assign them, right? And it might be a good idea to watch them quickly if you have time. But at the very least, to watch properties of solids, and then maybe solids, liquids, and gases. So once these three. And try out these 6 questions. This will be a good head start, and then tomorrow I'll go over these topics. All right, so have a fantastic day. I'm excited to get back into the classroom next week, so I will see you all next week, and have a great day, yeah?